going to be talking about 3D in the browser and mainly focusing on how these graphics are actually produced in your browser and not so much on Three.js and writing code, but more about the technical process about how things are passing from Three.js down to your GPU and onto your monitor. There's another tech talk that actually focuses on like the history of web graphics and 3D in the browser. It's titled Three.js. It's on the full stack page. If you want to take a look, I definitely encourage you to do so. So OpenGL, what is OpenGL? OpenGL is basically a 2D, 3D vector graphics API that lets programmers talk to directly to their GPU, basically. It's extremely low level, and it's very difficult to write code for. I'll show you very quickly. This is OpenGL code written in GLSL. If you write all of this code, you get basically just a blank page. Like this is just a canvas. So you have to write a lot of code before anything actually starts to work. So WebGL was written. And WebGL is a level of abstraction on top of OpenGL, which wraps OpenGL in JavaScript. It's cross-platform. It can run on any operating system. It runs on browser. It can run on mobile, on tablets. It does not require plugins. It comes default in most of your browsers. And it runs directly in your GPU. It is still very difficult to write code and produce graphics on your browser using WebGL. Here's some WebGL code. All of this code will produce this, a white box, right? Obviously, you wouldn't use WebGL or any of these 3D graphics APIs or libraries to draw a white box. The advantage comes in with 3D graphics. But the advantage with Three.js is it basically takes a lot of this WebGL functionality and it breaks it out into functions that are very easy to use. And you can write a lot of really cool web graphic code very quickly. So in WebGL, to draw a 3D cube like this, the code is like this. You kind of have to denote very specific vertices in 3D space. You have to write out their coordinates, and you get this 3D cube. In Three.js, this is the code. So it's much simpler. It's very easy to write code for WebGL and Three.js. But what I want to focus my talk on mainly is how all of this is working on your computer, right? How is what you write in Three.js making its way down to your GPU and onto your screen? So what's happening is you're writing your application in WebGL and it's running on your browser. Your WebGL application is communicating with an OpenGL framework that's running on your CPU and is a part of your operating system. When you buy a new GPU, a new graphics card for your computer, you install some custom drivers onto your computer. Those custom drivers are responsible for communicating with this OpenGL framework. So when you have your WebGL app, and it's passing instructions all the way down to your graphics card, your GPU, that's what's responsible for actually rendering the graphics onto your screen. So here's a good example. So how is this working? Basically, your computer is, the 3D space aspect of this is sort of an illusion, right? It's not actually 3D space, it's a 2D image. And the 2D image is constantly being calculated every 60th of a second, or you can get down to about 30 frames per second, but typically it's 60 frames per second on the browser. So every 60th of a second, it's recalculating this image and drawing it to your browser, right? So I want to talk for just a second about traditional render software. Before I came to full stack, I worked as a 3D artist for a number of years. And the software used for film and television is much different than what's running in your browser, right? It uses a method called ray tracing, which is extremely powerful. Basically what's happening is you have a camera object, and your camera is shooting rays out into your scene and collecting data and passing it back to the screen. And it's running calculations for every single pixel in your image. And each of these rays is collecting a ridiculous amount of data based on lighting, shadow, a ton of information is being collected and sent back to your screen and creating an image, right? Obviously, this is very powerful. You can get very, very like hyper-realistic images, but you can't run something like this in real time. It can't run on your browser, right? So OpenGL is making significant sacrifices in favor of performance. And it's important to understand this, I think, to understand why WebGL would make the decisions that it's making. Like why would it, or actually OpenGL, I should say, is making these decisions to render graphics the way that it's rendering them. And it's doing so because the user has to be able to interact with these graphics in real time, play games, this sort of stuff. And in film and television, you would never obviously need to interact with these graphics in real time. So rendering in the browser. So like I said, every 30 times per second, your browser has to recalculate the image based on maybe you move the camera, maybe an object in the scene moved, has to recalculate the image and bring it onto the screen, right? So how is it doing this? It's using a method called rasterization. So right down here, when your OpenGL is communicating with these drivers and to your GPU, it's breaking down your 3D scene into some data. And what a vector image is versus a raster image, vector graphics are basically mathematically produced graphics, right? I can reproduce this image on the right at any scale, and it will be mathematically reproduced for that scale. The image on the left is a raster image. Raster images can't be reproduced at larger scales. If it's a 500 by 500 pixel image, you can't increase it to like 10,000 by 10,000 pixels. It'll be really blurry and pixelated, right? So what rasterization is doing is it's calculating your image based on the 3D data in your scene, and it's turning it into a raster image that's being produced onto your computer monitor. And this is basically the OpenGL render pipeline, right? It's going into your 3D scene, it's collecting vertices on every face of every 3D object in your scene. It's breaking them apart. Each one of these vertices has data attached to it, so like a color data, a depth, a coordinate in 3D space. It's reassembling these data points into a 2D image, breaking them into triangles, and then filling in these triangles with pixel data. And it's saying, so basically, if you have one triangle that has red data information, blue, green, it's finding a way to blend all those colors together for every single triangle on your screen. And that's how it's figuring out what colors, what shadows, and this sort of stuff. And then it's doing all this stuff in your GPU and then sending it to your monitor. Yeah, so here's some examples. Some more cool examples. So here's some data visualization. The population of the Earth, I guess. So you can do some pretty intense things with WebGL. This is like a full game that someone made that runs real time in your browser. And you can fly around and stuff like that. Yeah. So I'll run through very quickly some Three.js code. Oh, sorry. Yeah. So Three.js makes all this very easy. You can create 3D objects and renders. It's a little small. Sorry about that. But basically up here, you're just you're initializing a scene. You're creating a camera object. This is all stuff that would take many lines of code, even in WebGL, but especially in OpenGL. You're telling you're rendering with WebGL. You're setting your canvas size, and basically what's happening is you're creating a canvas div that's being appended at the end of your HTML DOM. There's no DOM representation of the graphics in WebGL. It's just rendering inside this canvas element. And down here, you're creating some geometry, a box. You're assigning it a color. And in here, this is really what's telling your browser to re-render every 60th of a second. And what it's telling it to do right here is rotate the X and Y position and re-render the scene every 60th of a second. And the result is something like this. So yeah, that's 3D in the browser. Thank you.